Okay, gentlemen, we're going to go ahead and move on with the next topic. In this video, I'll go over the topic of what's called the law of cosines. The law of cosines is the second method that you might use in order to solve triangles that are not necessarily right triangles. That really, while you may have the law of sines in your arsenal of things that you can use, the law of sines requires that there's at least one angle side pair um, in order to solve the triangle using the law of sines. The law of cosines does not have that restriction, and so really any of the problems that you could solve using the law of sines, you could also solve using the law of cosines. But it's not the reverse, that you couldn't use the law of sines for every problem that you would use to solve the law of cosines because the law of cosines does not have that restriction of needing an angle side pair. The law of cosines is an equation that establishes the relationship between the side lengths and the angle measures of a triangle. In order to utilize the law of cosines, we have to at least be given three pieces of information, whether that's two sides in one angle, or three sides, or two angles in a side, and of course, one of them being a side measure. Um, it looks very daunting at first, the statement of the law of cosines, because there are three different forms of it. But the general structure of the law of cosines is that side one, side two, side three are distinguished between each other, um, and the angle opposite each side that's on the side of the equation by itself is the important piece of information. I know that's very vague and unclear, but what the law of cosines says is, let's say that this is like side one, side two, and side three. And here's like angle one, angle two, and angle three. What it says is that if I pick one specific side, square it, it must be the case that that's always equal to um, this side squared plus that side squared, and then subtract away some information, some piece of information that comes from the product of those two sides and the cosine of the angle between those two sides. And we'll work towards proving that idea here in the first video relating to the law of cosines. And in the second video, we'll do some more examples. So why don't we just go ahead and walk through the idea of the proof. I'll remind you that in this triangle, we're not told that it is a right triangle. In fact, it could be a non-right triangle, which is generally where we would use the law of sines or the law of cosines. But I could sketch in an altitude so that I can form two right triangles, kind of like I did in the proof of the law of sines. And then the second right triangle would be this red one here. And when I put those together, per se, I get the original triangle. From that information, I'll title this triangle 1 and then this other blue one triangle 2. I can use some of the theorems that I've learned this year in order to make some statements. For triangle 1, for instance, I know that the Pythagorean theorem would tell me that x squared plus h squared is equal to b squared. That this side length squared plus that side length, the altitude squared, is equal to b squared for that red triangle. And I can make a very similar statement for the second triangle, triangle 2, that a minus x squared plus h squared is equal to c squared. I guess I should pause for a second and make sure we understand the diagram too. What the diagram is saying is that this entire side length opposite angle A is side A. And if I call this little side length x, then the remainder, the leftover, would be a minus x. So for instance, as a numerical example, if the entire side length was 8, and for instance, this was 4, well, maybe not 4, this was 5, this piece over here would have to be 3. And how did I find that? I took the original side length and subtracted away the other one. And that's the general relationship that's shown right here. In order to get this side length here, in order to get this side length here, I took the whole thing and subtracted away the other piece. So proceeding forward, um, in triangle 2, I have that statement, a minus x squared plus h squared equals c squared. Well, that has some work that can be done to it. Particularly, I'm interested right now in the expression a minus x squared and how I might work with that. I'll remind you that that represents the product a minus x times a minus x. Oh, and I can FOIL using those Algebra 1 skills or Algebra 2 skills in order to produce a different expression. So multiply the firsts, a times a is a squared, the outers minus a times x, the inners minus a times x, and the last plus x squared. And then finally, I'm going to do some combining of like terms. A squared minus 2ax plus x squared. And that's the thing that will substitute in place of that expression we have right there. This is a squared minus 2ax plus x squared plus h squared. That's all we did, is replace that or substitute that expression, is equal to c squared. From there, I can do a little reorganizing, and I want you to keep in mind that the substitution property says that if I have some expression that I can establish in one piece, and I see that expression in another piece of a different equation, I can take the other piece of the other part and substitute that in for wherever I see, for instance, x squared plus h squared. And that's what I'm going to do right now. I'm going to use the substitution property to say, well, that must be the case that a squared minus 2ax plus b squared is equal to c squared. If you've got a keen eye, you might see the Pythagorean theorem in here. These two things are very closely related. I'll describe why. Well, it's because there are two right triangles, but that's the general relationship. Let's continue forward. I'm going to reorganize and move the b squared in front of the minus 2ax, and I'm going to move the c squared to the other side. C squared is equal to a squared plus b squared minus 2ax. And that looks very, very close to what the theorem I'm trying to prove looks like. This statement of the law of cosines. I want to replace this x with something, so I wonder if there's an expression that I can. And I'm going to take a step back to this original red triangle up here. If I look at angle C, from angle C, I can write an expression, a trig function, in terms of the adjacent side, and the hypotenuse. And what that would be is the cosine of angle C is equal to adjacent x over hypotenuse b. Or that if I multiply both sides by b, I get that x is equal to b times cosine of angle C. And now I have an expression, b cosine of C, that I can substitute in for x right here. So I'm going to do that. C squared is equal to a squared plus b squared minus 2a, and then x would be b cosine of angle C. And then lastly, multiplying out as necessary, I get c squared is equal to a squared plus b squared minus 2ab cosine of C. And that is the statement of the law of cosines, or one of the three at least. I should note that the other two are proven in the exact same way. You would just pick a different side and draw the altitude from it. That's the general relationship that you're expected to know. I don't expect you to know how to prove it. I wanted to walk you through the proof. I'm going to walk you through one example in this first video, and then the second video, I will do the rest of the examples. So let's go ahead and proceed forward with the next example. Using the information given in the diagram, solve for the value of r, where r is this side here. Well, the law of cosines would help me do that because I am given three pieces of information. I'm given this side, I'm given that side, and I'm given the angle between them. What the law of cosines might say is, well, if I'm given this angle here, perhaps it's conducive to use the form of the law of cosines that would um, correspond to the opposite side that I'm solving for, that r squared is equal to 45 squared plus 52 squared minus 2 times 45 times 52 times the cosine of 36. Being the case, that's just a matter of sticking it into your calculator in the correct form and getting an expression. R squared is equal to, and I know it's long, but you're able to work through it. Okay, I'm going to pull up my handy dandy calculator. Unfortunately, it's not visible to you guys. 45 squared plus 52 squared minus 2 times 45 times 52 times the cosine of 36. And I get that it's approximately equal to 942.8. So then how do I solve for r? I take the square root of both sides. R is equal to, and since this is a real number value, it's a side length, I'm only concerned with the positive square root. Um, where's the square root on this button or on this calculator? 942.8. So that R is approximately equal to 30.705. And since there is a unit there, well, I need to include the units, centimeters. To me, the law of cosines is fairly straightforward, that you're simply identifying the correct